From hubs to gateways, how data finds its way in the digital world. Have you ever wondered how your message travels from your phone in Honolulu to a server in Tokyo? Or how Netflix streams a movie so smoothly across millions of devices? The internet may seem like magic, but underneath the surface lies a structured network of devices that act like the post offices, traffic lights, and customs checkpoints of the digital world. Let's take a quick journey through the fundamental concepts of networking. Hubs, switches, bridges, routers, and gateways. At the most basic level, imagine a hub as a loudspeaker in a crowded room. Lit shouts every message to everyone, hoping the right person hears it. In early networks, hubs were used to connect multiple computers together, but they were simple and somewhat inefficient. Every piece of data, called a packet, sent to a hub, was broadcast to every connected device, even if it wasn't the intended recipient. It's like announcing, "Who left their coffee mug?" to the entire office, instead of just asking your deskmate. Then came the switch, the more intelligent version of the hub. A switch is like a receptionist who knows exactly where everyone's desk is. By the same token, a switch's intelligence lies in its ability to learn the network's geography. It maintains a MAC address table, sometimes called a Content Addressable Memory or CAM table. When a device first connects, the switch reads the unique physical address, MAC address, embedded in the packet and records which port that device is connected to. This targeted delivery dramatically reduces unnecessary traffic. Since data isn't broadcast everywhere, conversations between devices happen faster and don't compete for the same bandwidth, leading to greater network efficiency. Further, by sending data only to the intended recipient, a switch also offers a greater degree of privacy and security compared to a hub, where any device could potentially eavesdrop on all traffic. In modern networks, switches are everywhere. From small offices to massive data centers, quietly directing digital traffic behind the scenes. They are fundamental building blocks that allow thousands of devices to communicate quickly, privately, and simultaneously. Next in the evolution of networking devices is the bridge, which, as the name suggests, connects two separate network segments. Much like a literal bridge connects two islands. Its primary role is to ensure smooth communication between the segments while simultaneously filtering unnecessary traffic, thereby significantly improving performance. By segmenting the network, the bridge effectively breaks up a single, large collision domain into multiple smaller ones. This reduces the chance of data collisions and increases the effective bandwidth for all users. For instance, in a large office building, a bridge might logically separate the accounting department's network from the marketing department's. This segmentation ensures that the heavy, continuous data flow within accounting, such as database queries, doesn't slow down the marketing team's activities. However, the bridge still allows them to exchange files or access shared servers when needed, making the communication conditional and efficient. A router takes the idea of intelligent traffic management a crucial step further. It's the network's GPS system. While switches direct traffic within a local network using MAC addresses, routers specialize in directing data packets between different networks, which is known as inter-network communication. When a packet arrives, the router examines its destination IP address and consults its routing table to decide the best path for the information to travel. The best path isn't always the shortest physical distance. It might be the route with the least congestion, the fastest speed, or the most reliable connection. Routers are the essential device that allows your local network, like your home or office Wi-Fi, to connect to the massive web of the internet. They strip off the local MAC address information and manage the data based solely on the global IP address. When you send an email from your laptop to someone overseas, multiple routers act like digital air traffic controllers. Each router along the way determines the next logical hop, ensuring your data finds the quickest and safest route. These devices keep the massive, global exchange of information moving seamlessly, transparently handling complex decisions about pathways and traffic load every millisecond. Finally, we arrive at the gateway. While routers connect different networks that use the same underlying protocols, like IP, the gateway is essential for connecting networks that speak different languages or utilize entirely distinct communication protocols. It is the most comprehensive and powerful connection point, acting like an international customs officer or a universal translator. A gateway, which is often a router, a server, or a firewall configured to perform these tasks, sits at the boundary between two disparate network environments. Its core function is protocol translation. The gateway repackages, converts, and manages data formats and protocols so that devices using one system can communicate meaningfully with devices using a completely different system. The most common and vital example is the connection between your company's private internal network, LAN, and the public Internet. The Internet uses a standard suite of protocols, TCP/IP, but your internal systems might rely on proprietary or slightly altered internal standards for security and efficiency. The gateway translates and manages that crucial interaction. Without gateways, your private LAN would be isolated, a self-contained island of data unable to talk to the global web or interact with external services. The gateway is the single, essential exit and entry point that makes global, seamless digital communication possible. Networks achieve robustness, the ability to maintain function despite failures, primarily through redundancy. This concept is best understood by looking at the intricate systems in the natural world, like the circulatory system in the human body. Imagine the dense, branching network of your blood vessels. If a single vein or small artery becomes blocked or damaged, your body doesn't shut down. Instead, the blood can continue to flow by diverting through alternate routes, collateral circulation, around the blockage. The sheer number of interconnected pathways ensures that the essential task, delivering oxygen and nutrients, is completed. By the same token, a well-designed digital network operates on this exact principle. If a critical component like a router or a switch goes down, other neighboring devices are configured to pick up the slack by rerouting data traffic. This rapid and automatic failover mechanism ensures that the network continues to function smoothly. Often, a user won't even realize a piece of malfunctioning gear exists because the service remains uninterrupted. Redundancy acts as a constant, invisible safety net. From shouting hubs to multilingual gateways, these networking devices form the invisible infrastructure that keeps our digital world connected. So next time your video call or game runs smoothly, remember there's an intricate choreography of hardware making it happen. What do you think? Which part of networking seems most fascinating to you? The speed of switches, the intelligence of routers, or the adaptability of gateways? Share your thoughts in the comments below. Thank you for watching. Mahalo!